infrastructure creators in the country who are making use of country's own resources, so to say. And there's a company called IOTA. So they're competing with AWS, Azure, Google Cloud, and so on, and doing well. So now in NLP, we're extremely hungry for computing resources. It will be useful to look at what they're doing. They're planning to create what is called a virtual AI lab, okay, where students can do their computation virtually. So let's see what they have to say. But before that, as you know, we have been discussing hypothesis testing after doing machine translation evaluation. So this is our usual one slide recap last week. On Monday, Nihar talked about bias detection, hallucination detection, also mitigation. They're a very important problem in today's large language models. And he covered mainly conceptual ideas and so on. Their implementation will be next semester when we do deep learning for NLP. So last week we did language divergence, and there are two kinds of divergence, as you know, structural and lexicosemantic. So in structural divergence, the difference is absolutely apparent. For example, in Indian languages, the verb go to the end. In English, the verb sits in the middle between subject and object. And this is probably the most important structural divergence. And then we have prepositions in English, postpositions in Indian languages. Okay, yeah. So can you wait for some time? I'll speak for about 40 minutes and then, yeah. Sure. So about this divergence, preposition, postposition, subject, verb, object, verb. These are structural divergences. Lexical divergences are due to vocabulary difference. So stab, for example, in English becomes chure se marna. Advice in English becomes salah dena, paramarsh dena. So this is called lexicosemantic divergence. Okay, so divergence study is fundamental for machine translation because it is this gap that we have to close by making use of data, resources, machine learning, and so on. Now, a very, very instructive exercise that we did was step-by-step systematic development of the blue score, okay, which has been the main metric for evaluating machine translation output quality. Okay, and the output quality will be good if the divergence is closed, right? So if subject, verb, object gets transformed into subject, object, verb, okay, then we have closed one structural divergence. And this is captured by means of the blue score. Blue score, as you know, goes from unigram, bigram, trigram up to quadrigram. Quadrigram matching keeps track of the syntax overlap. Okay, so the machine translation output is a string of words, and it is compared with the reference translation, which has been created by expert human translators. Okay, so it is essentially a matching exercise. And in the matching exercise, we compare unigrams and bigrams. Unigrams take care of lexical overlap. Bigrams mainly take care of multi-words. Trigram and quadrigram take care of syntactic overlap. Okay, so this is the scenario, and in the blue score, as you see, the formula is BP, which is brevity penalty. Brevity penalty is introduced because if the translation output is very short, then there is a high chance that everything in that translation output will match the reference translation. So if the translation output is short, then there is a brevity penalty. Then you have an expression e to the power sigma n equal to small 1 to capital N, W1 log Pn, which is essentially geometrical mean if all Wn's are equal. Okay, and remember that all these Wn's n equal to 1 to capital N have to sum to 1. Okay, so if you want to give more importance to quadrigrams, you insist that syntax matching takes place, then W4 would be more than W1 and W2 and W3. However, W1 plus W2 plus W3 plus W4 has to be equal to 1. Okay, so this is essentially geometric mean if W and N's are all equal. And geometric mean is in between harmonic mean and arithmetic mean. Harmonic mean gives importance to the lowest of the scores. Arithmetic mean gives importance to the highest of the scores. So this is a balance, okay, between highest and lowest. And this formula has come to stay. The core of the formula is Pn, okay, which is the ratio of how many n-grams are matching divided by number of n-grams in the candidate translation, the machine translation output. So this is a precision-oriented metric. When we give importance to recall, that is, we give importance to n-grams in the reference translation, then we have another score, it is called Roux score. Roux score has been used extensively in summarization. So I have posed a problem for you that why should recall-oriented score be important for summarization, whereas precision-oriented score is important for translation. Okay, so this is a conceptual question, and it requires understanding machine translation as a task, summarization as a task, and the matrix of Roux score and Roux score. All these four things have to be understood to understand why recall is important for summarization, whereas precision is important for translation. Okay. Then we started introducing probability in our discussion. We wanted to discuss this very well-known problem in probability and statistics, the bridge breaking problem. What is the safe number of cars on a bridge so that the bridge will not break? Okay, to a very small number of bridge, no risk. But this is not economical. This is not the full utilization of the facility. If there are too many cars on the bridge, yes, full utilization, very good collection for the government from toll tax, but there is high risk to the bridge. So something in between has to be found out. What is that number? We are trying to derive it by making use of probability. And the instructive thing here is that we have to make use of probability for doing so. Okay, for solving this task, probability is the correct instrument to use, and that also has a lot of correspondence with what we do in natural language processing. So that correspondence I'll show you, but first let me discuss the bridge breaking problem. So so the practical problem is that the bridge is being built. The weight it can tolerate has a distribution with mu equal to 400 and sigma equal to 40. So this is the start of introduction of probability. So let me give you a more dramatic statement. You might find it a bit strange, but those of you who have done quantum mechanics maybe will not find it so strange after all. Okay, in quantum mechanics we know that elements have both particle nature and wave nature. Okay, an element can be in the form of a wave function, okay, or it can be a particle, light particles, for example. So the particle nature is invoked to explain photoelectric effect, for example, the generation of electricity from light. On the other hand, if you want to explain dispersion, okay, the band that is produced when light passes and there is an edge. So there you have to invoke the wave nature of light particle. Okay. Now this is extended and it is said that everything in the universe has a wave nature associated with. I also have a wave. Okay. And just at the risk of sounding a bit strange, you'll probably accept the fact that there is a concentration of the wave function associated with me here in LA001 on this stage. Okay, but there is a probability distribution as to where I am currently. So I am also present in my office with a small probability right now. I am present at my home with a small probability right now. You will find it strange. But why so? Because you're seeing me in front of you. But this is actually true. Okay, actually, a part of my mind is in my office. Okay, did I lock my door? A part of my mind is at home also. What time can I go home? Will there be traffic on the road? And so on. Okay, so there is a notion of distribution associated with everything. We have to change our conceptual ideas. We have to change our thinking a bit to accept this, new way of looking at the actions and things in the world. So NLP is very much dependent on probabilistic setting. And since probability parameters are estimated from data, that's why we need a lot of computing resource, a lot of data to have those parameters estimated accurately. So now here the bridge is being built and the weight that it can tolerate, the tolerance level is not a single number, which is the most important point to note here. It's a distribution, normal distribution, with mean as 400 and standard deviation as 40. The car's weight is also a distribution. Both these are easy to understand. Okay, so the car's weight is a normal distribution with mean as 3 and standard deviation as 0.3. So 1 sigma distance from the mean would be 3.3 and 2.7. Okay, for the car. 1 sigma distance for the tolerance level will be 440 and 360 for the bridge. Okay, 1 sigma distance. So we make use of this to have first a deterministic approach to solving how many cars can be on the bridge, and then a probabilistic approach. The probabilistic approach is more accurate. We have to see why. So we want the probability of damage to the bridge to be less than 0.1. The other point is that the question of determinism does not arise here, as you can see. Okay, if you say that if 120 cars, if they go on the bridge, at the 121st car, the bridge will break. Not true. Not true. Okay, it can sustain, probably it will not break. And suddenly one day you find that it breaks. So all these situations are inherently probabilistic. Okay, so that's why we have to invoke probability, we have to appeal to probability and say that the probability of damage to the bridge has to be less than 0.1. Okay, so our requirement also has to be probabilistic. The probability of damage to the bridge has to be less than 1. And how many cars can we now allow to go on the bridge? This question is so similar to asking, how much of data do I need so that my machine learning model does sentiment analysis with accuracy of 90%, and my confidence in 90% will be 95%. Always two probabilities are involved. Okay, the probability of sentiment analysis accuracy is probabilistic. Okay, that is because when the sentiment decision is obtained, this is obtained in the form of a softmax function, which is a probability distribution. And the value that I'm seeing for accuracy, I have some confidence in this, which is also probabilistic. Okay, so it is a very typical situation in machine learning that you almost always have two probabilities in accuracy and confidence. They almost always go together. How did it come into being in machine learning? It came through a framework called PAC, probably approximately correct learning, 1984, Leslie Valiant from Harvard University. Okay? And because of this very fundamental paradigm coming into machine learning, he got the Turing Award. I don't remember the year, but this has had profound influence on machine learning. The fact that two probabilities are always two, accuracy, confidence, is also called probably approximately correct learning. Okay, so I definitely insist that you look at this paper. This paper is in theory of the learnable, by LG Valiant. LG Valiant, I think it is CACM. Communication Services. I will definitely about the year because my PhD was in this area, fact area. So I think the journal is CSA, a theory of the learning. This is a must read for any machine learning researcher. And as you know, this particular course is more concept and foundation oriented. The next course, DL for NLP, is more technique oriented. So I insist that you get these foundations very strongly in place. So two probabilities, okay? So here also there are two probabilities. The tolerance is a probability distribution. Car weight is a probability distribution. The guarantee for safety is also probabilistic. Okay, everywhere probability. So now let's see, when does the bridge break? The bridge breaks when W total exceeds the W tolerance. Is it correct? No, it's not correct. If W total exceeds the W tolerance, the bridge may not break. Okay, so when W total exceeds W tolerance, there is a high probability that the bridge will break. See how probability comes in. Bridge will break is deterministic. With high probability the bridge will break is a probabilistic statement, which is more correct. May not break. Okay, in language also, will I see a noun after adjective? Most of the time, but not always. Okay, what is the meaning of bank? Is it the bank or the river bank? Most of the time, financial bank, but not always. Okay, so this not always is basic to whole of AI, and that it requires probability to be used as an instrument. So W total greater than W tolerance is for our understanding, in our limited understanding. Actually, there should be a probability measure, probability associated with that the probability of W total being greater than W tolerance is so and so, which is different from this statement. It is inaccurate. So we take a deterministic approach. The bridge will damage. First, we concentrate only on the mean value. So let's say there are n cars which are allowed on the bridge. Now 3n equal to 400. 3 into n is equal to 400. We are comparing only means. So that gives me n equal to 133. So I'm saying that if there are 133 cars on the bridge, then the bridge will break. It is a rough estimate, very naive estimate, okay, but a good starting point. Then I take the best possible scenario. The strongest bridge and the lightest car. The strongest bridge will be 1 sigma more than the mean value. That's my assumption. So 400 mean plus 41 sigma. So 440, and the car weight is 2.7. Mean minus 1 sigma, which is 2.7. So the most liberal situation, also the most risky, is this. The ceiling of 2.7 n equal to 440, which gives me n equal to 163. Okay, mean comparison gave me 133, now it is 163. 30 more cars can go, but risk also increases. Then we come to this situation, the most conservative. Assume that the bridge is the weakest. So the bridge can withstand mean minus 1 sigma weight, which is 360. And car weight is also maximum, which is mean plus 1 sigma, which is 3.3. So this is most conservative situation and the safest, but resource-wise most inefficient. So floor of 3.3 n equal to 360. This gives me n equal to 109. So it is less than the number that we got from mean comparison. So we have three numbers: 109, 133, 163. What is the number of cars I will allow? Okay, the city authorities have to make that decision. But the thing is that all this is not very principled. Okay, principle comes from probability. Okay, so what is the methodology? Methodology is that we need a balance The sweet spot is somewhere in between, the middle path. The answer is probability. So the whole problem is really a multi-objective optimization. Many objectives to be satisfied. Safety first, then utilization of facility, earning for the city authorities, people satisfaction, and so on. Now we bring in probability. Let the number of cars be n. Okay, that is the number that is allowed on the bridge. See the formulation of the problem, which is instructive. Each car's weight is normal with mu equal to 3 and sigma equal to 0.3. Now we have to invoke what is called the central limit theorem. Okay, the statement of the central limit theorem we'll see later. But the consequence of central limit theorem is that the sum of Gaussian random variables is Gaussian with mean and variance being sums of individual means and variances. This is central limit theorem. Okay, the sum of Gaussian random variables is Gaussian. This itself is Gaussian with mean equal to sum of the individual means and variance being the sum of variance. So recall that recall that the car's mean weight is 3 and the variance is 0.3 square, which is 0.09. So the sum of the weights of the cars on the bridge, that also will be normally distributed. Its mean will be equal to 3n. 3 plus 3 plus 3 up to n times. And sigma squared, the variance will be 0.09 into n. Good. Okay, so the total weight on the bridge has been now cast into a normal distribution in terms of n. 3n mean and 0.09 n variance. Okay, fine. So W tolerance looks like this, fine. Now the bridge is damaged when W total is greater than W tolerance. That is W total minus W tolerance is greater than 0. So now we want what is the total number of cars that will cause the probability of damage to exceed 0.01. So we are interested in this probability expression, probability of W total minus W tolerance. The probability of W total minus W tolerance to be greater than 0 should be greater than 0.0. So there is a missing value there. Okay, so the probability of W total exceeding W tolerance should be greater than 0.01. Okay, I'll correct that expression. So the LHS is a function of n and W total is also a function of n by central limit theorem. So now let's work with this expression, okay, for another 15 minutes or so. So the meaning of probability W total minus W tolerance greater than 0 to be greater than 0.1. Let n unsafe be the limit on the number of cars allowed on the bridge. So what does this mean? This probability expression. Out of 1,000 cases of the bridge allowing n unsafe cars to pass over it, in more than 10 cases, the bridge will break. Okay, so that is the meaning of this probability exceeding 0.1. Okay, so if we take a limiting case where 1,000 is a good number, so if we allow 1,000 cases of the bridge allowing unsafe number of cars, then in 10 cases the bridge will break. Okay, that is the probability I want. Okay, if I do not allow unsafe number of cars on the bridge, okay, even then the bridge can break. Okay, if everything is probabilistic. But what I want is that if I allow unsafe number of cars to be on the bridge, the probability of the unsafe number of cars should be such that the probability of the bridge breaking should be 0.1. Okay, let's analyze this further. So let's examine this quantity W total minus W tolerance. This is also a random variable. Now again by central limit theorem, this is the difference of two normally distributed random variables. That difference is also normally distributed. Again, a consequence of the central limit theorem. Okay, so the mean will be 3n minus 400 of this random variable. W total minus W tolerance is a random variable. Okay, so the mean is 3n minus 400 by central limit theorem. So the interesting thing is that when we take subtraction of two normally distributed random variables, their variances add up. Okay, their variances do not subtract. Their variances add up. So for this quantity, W total minus W tolerance, the mean is 3n minus 400, and the variance is 0.09n plus 1600. 1600 is 40 square. Okay, that's why 1600. So this W total minus W tolerance now is a normally distributed random variable for which the parameters are known. We know the variance, we know the mean also. Now let's see how to proceed. We are interested in the value n. So we would like to convert this random variable into the standard normal form. So for that, the procedure is that we have to subtract the mean and divide it by the standard deviation. So W total minus W tolerance is a normally distributed random variable whose mean is 3n minus 400 subtracted, divided by the standard deviation, which is 0.09n plus 1600 square root. So now this is a standard normal form whose mean is 0, standard deviation is 1. Okay. We convert into this form because of the availability of what is called the Z-score table. Okay. Okay, let us see. So we want this event W total minus W tolerance to be greater than 0 to have low probability. Okay, so consider this inequality. W total minus W tolerance is greater than 0. We subtract 3n minus 400 from both sides and divide it by 0.0n plus 1600 square root on both sides. Okay, then what we have is that the standard normal variable z should be greater than minus 3n plus 400 divided by square root of 0.09n plus 1600. Okay, as you see on the screen. So from this, where we go, z should be greater than this quantity. Now, probability of z becoming greater than this quantity, for what value of n does it exceed 0.1? Okay, this is the question. So we are interested in this expression, and solving this will give me n less than or equal to 170. How so? We have to use what is called the Z-score table. Okay, that is because we are interested in this quantity. Probability that Z is less than B for normal distribution is given in this form. Minus infinity to V integral 1 by 2 pi e to the power minus y square by 2 dy. Y is a standard normal variable with mean 0 and standard deviation 1. Okay, so when mean becomes 0 and standard deviation is 1, the normal distributions form is e to the power minus y square by 2, y is standard normal distribution, 1 by 2 pi. Okay, So this is a normal distribution with mean 0 and standard deviation 1. So the area under the curve from minus infinity to V is integration of this quantity. Okay. Now we want the probability of Z exceeding V. So this will be equal to 1 minus probability Z less than B. Okay. Probability of Z less than B. Since we want probability of Z greater than B to be greater than 0.1, we're interested in this quantity. Probability of Z less than B should be less than or equal to 0.9. Okay. So for what value is the area under the curve, standard normal curve, 0.9? For what value of B, V, you get this probability as less than or equal to 0.9. So this comes out from this figure here. So this is called the Z table. I think it is clear on the screen. It's not very clear to me because it was very small. So the area that is of interest to us is the area under the standard normal curve, okay, whose value is equal to 0.9. So from minus infinity to a value such that the area is 0.9. So that V value comes out to be 1.28. Okay, you can read it from the Z-score table. I'll show you how to read it. You have to make use of the column and the rows. Okay. Now, if we found that V is 1.28, how do I use it? So we want 1.28 to be equal to minus 3n minus 400 divided by square root of 1600 plus 0.09n. So for solving for n, I get n is approximately equal to 170. So most liberal estimate gave me 163. Equalizing the means gave me a value of 133. Most conservative estimate gave me 109. And the probabilistic treatment gives me 170. Okay. So, so that we have to analyze these numbers. One 117, 133, 163. Liberal, conservative, realizing mean, T damage, these are the four treatments. Okay. And this is most realistic and most principal. I can guarantee a probabilistic bound. I can give a probabilistic guarantee for the breach to break by this analysis, the method of analysis that I showed, where you have to consult the Z table, turn the variable of interest into a standard normal form, and then get the numbers. Okay. So can you give me these pictures? Right. So this is how we approach the problem making use of probability. Okay. Conservative, probabilistic, deterministic, equalizing mean, deterministic, liberal. So the summary of all this analysis is that if we allow more than 117 cars on the bridge, then in 10 out of 1,000 cases, the bridge will break. Okay, that is the conclusion from this summary. The slides will be with you. Just go through this again. I'll come back to this method of analysis again and again. So in remaining 4 minutes, let me just introduce the terminology for test of hypothesis. Is everything okay there on the screen? A very important concept is called null hypothesis. Okay, the hypothesis we want to reject. HA or H1 is called the alternative hypothesis, which is the opposite of H0. And we use sample statistics trying to reject H0. So let me illustrate this method of rejection in the face of a hypothesis. This is a digression. Hypothesis testing in logic. Okay, this example tells us very clearly how hypothesis gets rejected in the face of observation. So this is an example which I always give in my AI class. Next semester I'll teach the third year undergraduate AI class. Okay, and when I do logic, this will come, and it shows clearly how what we observe can refute the hypothesis. Okay, here's an interesting problem. A, B, and C belong to a club called Himalayan Club. This example is from a book called Theory of Computation by Zohar Manna. A, B, and C belong to the Himalayan Club. Every member in the club is either a mountain climber or a skier or both. There is no other option. Every member has to be a mountain climber or a skier or both. A likes whatever B dislikes and dislikes whatever B likes. Okay, they are kind of sworn enemies, let's say. A likes rain and snow. No mountain climber likes rain. Every skier likes snow. Is there a member who is a mountain climber and not a skier? Is there a member in the club who is a mountain climber and not a skier? Okay. So these are the facts and observations given to me. To answer this, we go take the path of refutation. We say that there is no such mountain climber. I mean, there is no such member who is a mountain climber and not a skier. So what will happen is that if we do so, if we assume that, then we'll come to what is called a contradiction. Okay, so this is called the resolution tree. And at the end, we get an empty box, which is called the null clause. Okay, this is what Prolog does internally, for example. So what is happening is that if I assume that there is nobody in the club who is a mountain climber and not a skier, then this hypothesis will lead to a contradiction with respect to the observation I have made. Now, observation or the data in front of me cannot be wrong. The data is real. Data is data. Then we have to throw away the hypothesis. So the hypothesis which is thrown away is called a null hypothesis because we are nullifying that hypothesis. Okay, so this is a very, very important tool of analysis for us. We would like to go deep into hypothesis testing. It will be the bread and butter for any machine learning research. Let's do that. Okay.